Hi, good afternoon. This is Mr. Cassidy, and today we'll be covering 8.1 and 8.2. And some of you are like, wait, what about Chapter 7? Chapter 7, we're putting on hold. We might cover little bits of it later on in the year, but our goal is to sort of get into some of the deeper stuff that's important for IM2 preparation. And so that meant jumping ahead to Chapter 8. So if you want to follow along in your journal, go ahead and open to 8.1. I don't have the page number in front of me, but several of the problems we'll be doing are from your journal, so you should probably have it out. Let's begin. Chapter 8, Lesson 1 is all about vocab. And it's really important that you take notes that are needed and follow along. Really make sure you're paying attention because it's very detail specific. And each problem and answer is going to require really a clear understanding of the details. And what we're going to talk about are points, lines, and planes. So let's jump into it. We're sort of talking abstractly about geometry. So if you find page 216, actually, that would be a good place to start. Exploration 2, we're going to find some examples in the room. And so here you've got sort of an example of two planes. What we call is a plane is a flat surface. If you imagine like a folder, just like there. Now, planes, though, do extend infinitely. So this plane would carry on. We just sort of draw it with the boundary to show that just to show it on paper, but the plane itself extends infinitely. Here we've got another plane and we've got a line and some points. And the idea is that we could even see these things in real life. So, for example, two lines can intersect at a point, they could overlap. So, here's our point, here's them overlapping, and here's them not intersecting. So, yeah, this is our idea about lines. So see, look around you right now. Are there any lines you can see that meet all three of those possible options? Um, I'm looking straight ahead at my fridge, and it's got upright handles that are the not intersecting lines. Now, again, when we talk about a line in geometry, we're sort of talking about the idea that that line can go on forever, never ending. And so every line we talk about is sort of this abstract, just infinite, straight, flat line. Next, we have a line and a plane. Now, they can intersect a little differently. So, a plane, if you imagine like a notebook flat on the table, and a line like a pen or a straw, like cutting through the table and then shooting straight up, it would only intersect at one point. If you imagine the table surface or the desk surface in front of you, and you had, I don't know, a drill and you tried to go drill straight through it, notice that that would only intersect at one point. A line can also be on a plane, which means it intersects infinitely, sort of like overlapping. And then a line can also be separate from a plane. So here's a plane and here's the line off of it, and it never intersects. Think like if you drew a line on your floor, say this was on the floor, any line on the floor, and here we have a desktop. Notice that those are never going to intersect. Our last idea is how two planes interact. So two planes can intersect in the same way. Two planes that intersect form a line. Look around you, see if you can find two planes that intersect in the room you're in. I think of like the wall and the floor. Notice they intersect at a straight line. They form a line. Two planes can overlap, so they can be just infinitely intersecting, like I don't know, two boards part of your table. There's a tabletop. And they could also be separate. Let's say this is your tabletop and this is your floor. They could also never intersect. They're sort of like parallel lines. They are infinitely extended. Even if they extended infinitely, or the ceiling and the floor, they would never intersect if they're following that same exact direction. So now that we've explored these ideas, we need to understand some definitions. In your text, this is on page 380. Your journal, it's page 219, and you really want to follow along here. So these are some informal definitions, and we sort of have an understanding of what they mean. A point has no dimension. A dot represents a point. It's like a single point in space, but if we're thinking of it as being this minuscule point, like almost like an atom or even smaller, it's just the single location it is represented, and we call that a point. A line has one dimension. It's represented by a line with two arrowheads, but it extends without end. Through any 2 points, there is exactly one line. So if you drew, and imagine this, imagine drawing 2 points any which way that you could. Can you draw a line through them? Well, yeah, you can. No matter what, no matter how you draw 2 points, at least in Euclidean geometry, and some of you guys are like, what about non-Euclidean geometry? I'm not going to answer questions about that. That's above my pay grade. Or at least it's above my head for the most part. So through any 2 points, we have a straight line. If you draw any 2 points and imagine any two fixed locations in space, like imagine the room around you, could you connect them by a line? You probably could. And now a line extends infinitely. That's what we mean by the arrows on the end. Now, there's two ways we can write a line. So here we have line AB. What we do, sorry, I'll have to cut this from our video. Hold on. Shh. She's not here. Sorry. I'm doing the video. Yeah, I need it quiet. Thanks. All right. So we have different ways we can refer to a line. A line can have a letter's name, and sometimes we call it like line L. And a lot of times that would be written in cursive. So if you see a cursive letter next to a line, like here, I'll put the letter M in cursive, something like that. I don't know, I haven't written in cursive in a long time. That would be line M. Okay. Now we can also call a line by its points. And here's the tricky part is if you put points C and D and you're going to name that line that extends through them, remember it goes past each point on infinitely. So we're going to put the arrows on this little like line symbol that goes above the letters. And that means we can also reverse the letters DC, and that would be naming the line because it still just means the line extending through points C and D. So the first key idea that I want you to really pay attention to is that's how we denote lines. We also can denote planes. Now a plane can have a letter name and it's usually capitalized. So if I say plane M, that means this plane here. We can also name it by points that are not on the same line. So notice that A, B, and C, if I drew a line here, they are not on the same line. That's what it takes. You sort of need two on a line and then one off the line for it to be a plane, because all three of those now exist on a flat surface of 2 dimensions. And so we call that a plane. Again, the idea of planes, they extend without end, and we can also call them by the 3 letters. The order doesn't matter. I usually pick alphabetical, but we just name it by the letters, or we just have the capital letter. Now, what does collinear mean? Collinear means on the same line. So if I put another letter here and it's E, all 3 letters, C, E, D, are collinear. How about coplanar? Well, coplanar might mean 2 lines that are on the same plane. It could mean the 3 different points that are on the same plane. It just means on the same. So co usually means same. So coplanar means we're looking for same plane. Carrying on with definitions. Define terms segment and ray. Now, first off, we already know a line can be named with its 2 points. We write its 2 points and we use the line symbol, which means extending infinitely. A line segment has endpoints. So to write a line segment, we're going to use the 2 points that are its endpoints, and we're going to put the line above it, but instead of the arrows, no arrows. Without the arrows, that means we're talking about just the chunk between A and B. Now you can name it either way. You could name it from A to B or B to A. But anybody who looks at it and sees just that little line above it knows that we're just talking about this chunk, not the line that's extending infinitely. We're talking about the line segment. Next is array. Array is extending in one direction from an endpoint. Now, to name array, we always start with the letter of the endpoint. So A would be the endpoint because it's the beginning. Endpoint, I guess, also means beginning in this instance, even though I guess that's counterintuitive. And we want to say that it goes past B. So what we're going to do is start from A and go past B. And usually we write rays left to right, so we use the arrow. So if you wanted to name this same ray down here, you would do BA, and you'd still do the line to the right because we're starting from point B and going to A and extending infinitely. Okay, now we can also talk about opposite rays. So here, CA, starting from endpoint C and going to A with the arrow, is the ray that starts here and goes this way. I'm talking about the ray there. Now, an opposite ray would be the opposite direction, right? So in this case, it would start from C and go through letter B. So that would be start at C, go through letter B, ray, arrow. And now all of these are very tiny differences. The little arrows on top, whether it's just a flat line, or the arrows at the end, whether it's a ray, it helps to be clear about what they mean. So first, let's just name some parts of this. You could name the plane. Okay, how about name which of these is a point? I'll just give you a few questions here to help check your understanding. And let's carry on. So here's some problems. Oh, so one question that may come up is RLN, and notice that that is a line segment. LN, we would just be talking about that section there. And UH perpendicular. Now, one thing I would mention, notice the dashed line here shows that L is actually going through the plane. It's not on the plane. Now, are they perpendicular? You might say yes, because they look like they might be, but it's not necessarily. The only way we denote something as perpendicular is if it has the square in geometry. When we have the square for a right corner, that means we know it's perpendicular. Okay? All right, give two other names for CD. So go and try this. Problem 1. Give two other names for CD. Notice we're talking about the line here because there are arrows on the end. Okay, so you should have said line M, and you should have also said line DC with arrows at the end. Give another name for plane M. You should pick the answer for plane with points A, B, and E. That can be written plane ABE, just with the 3 points. Name 3 points that are collinear. You should have said A, C, and B. Then name a 4th point that is not collinear. You could say B or D, because those are not collinear with all 3 of those points. Name a point that is not coplanar with A, C, and E. You should have said point D. Okay, moving on. All right, what's another name for PQ? Notice we're talking about the line here. Now you actually have a lot of different answers there. You could say PT, TQ, QP, line J. All of those are possibilities. What's another name for RS? Again, lots of possibilities. Number 7, name all the rays with endpoint T. Okay, there's tons of answers here because you could say TR, with the arrow that way, right? That's from T going to R and past. We could say TQ. We could say TP. We could say TS. All of those are rays with the endpoint T. On the diagram, draw planes M and N that intersect at line K. The drawings may be a little tricky. I've got a little instructional on that, but basically for planes, you draw sort of parallelograms like this. And if you're going to draw two planes, you sort of try to do another one that's like upright. So you sort of like go like this and maybe show when it goes behind something with a dashed line. And so I just go further. And then when it's a dashed line until it intersects and then goes up. And technically, this back one should then become a dashed line, so I would then erase. Right, so moving on. Some intersection ideas, we've gone over this. Sketching intersections, here's some ideas here if you want to look them over. I'm going to move on. There's a tiny bit more. Complete 9 and 10 on page 220, sketch this. Number 9, notice they want us to sketch a line segment AB and array BC. Well, they have to share point B. So here's one way to do it. You could have made that ray go continue on straight. It could have gone down. Either way would have, as long as C is down here or on this next chunk, you'd be fine. How about line K in plane M? Well, here we just draw a plane, labeled M, and we put the line on the plane. Okay, and if the line is in the plane, then the whole line is part of the plane. We're going to carry on to chapter 8, lesson 2 with this lesson. So follow along, continue to follow along. If we were to measure this, we would say that this caret is 1, 2, 3, 4, 5, 6, 7 centimeters. But what if it was here? Well, you guys have probably done math like this, right? You've looked at a ruler and been like, okay, I didn't quite line things up right, but I can just know that, well, 10 take away 3, 10 minus 3 would give me my answer, 7. 7 units. Well, we're going to be using this idea, and it's called the ruler postulate and the segment addition postulate in this lesson. First idea might be just some practice, some math practice. Simplifying the expression means we're going to simplify the inside first. -3 plus -1 is a -4. Then we would apply the absolute value. Absolute value just means distance, so we would use +4. Go ahead and solve maybe problems 2 and 3. Okay, 2 you should have gotten +1, and 3 you should have gotten +2. Okay, all right. How about 4, 5, and 6? And I'm just moving quickly here. This one should have been 10. The next one should have been +4. And the last one should have been +22. Remember, all your answers are positive because the absolute value happens last. In geometry, a rule that's accepted without proof is called a postulate. And we're starting to get into geometry this chapter. The ruler postulate shows how to find distance between 2 points on a line. So let's say we had to measure the distance between 2, 3 and -1, 3 on this line. So 2, 3 would be here on the graph. -1, 3 would be here. And what we would do is we would just count up the units, the square units in between. This is 3 square units. So the measurement here is 3 square units. Well, there is another way we can sort of use the ruler postulate, like the measurement idea. Notice that this goes from x is 2 to x is -1. We can go 2 minus -1. And sort of like the problems before that, when we take the difference and put the absolute value, we get the distance. So we take the difference, take the absolute value. 2 minus -1 is 3. And the absolute value of 3 is 3. Okay, so here is the actual formal definition of the ruler postulate. Guys, all the work with this is super simple, so just get ready for it. All right, so the real number that corresponds to a point is the coordinate of the point, and we can do the difference between those coordinates to get their value. So we just do the absolute value of their difference to get their value of the distance. Okay. So congruent segments is another idea. We talk about line segments here. Notice we've got just the line segment designation, meaning we've got the flat line on top. And the way we say congruent is we say that two lines are congruent when they are equal in length. Tiny little bit of detail here is notice there's no line segment note here when we're talking about length. We just say AB equals CD. That means those chunks are equal in length. Now to talk about the line segments, the geometry part, that's where we're going to use that line segment designation. We're going to use this congruency symbol. AB is congruent. It's an equal sign with a tilde or a little wavy line on the top. Is congruent with CD, and that's where we're going to say both line segments. Now, don't get too hung up on this. Really, most of the work we're going to be doing is using this, where we put the line segment mark and we put the congruency mark. Also, we can draw anything. If I were to draw a triangle that is equilateral, I can put these things called tick marks. A tick mark designates that that is an equal length or congruent segment. Let's say I have a rectangle. The way I would designate that the two sides are corresponding, here this side is corresponding with this, but then I'm going to move on to two tick marks here to make those congruent. And that sort of shows me that the top and the bottom are equal to the left and the right sides. Last, we have our idea for the segment addition postulate. All the segment addition postulate is just saying is if we have B in between, then if this one is like 5 and this one's 3, then the whole thing's 8. That's all it is. Okay, if B is between A and C, then the sum of them is the total of the length. Right, and here's how we might use that. We put a point in between the other two, and notice that that only works when they are collinear. If point E is off it, if it's coplanar, if it's off that plane, off that line, I can't use segment addition because these diagonal lengths are actually going to be more than the length that's straight between D and F in sum. So here's our first idea. Are the lines segments congruent? You're going to draw them on the graph and decide. So problem 1, go ahead and draw it and decide. You should have said yes. When you draw the two line segments, you can use that ruler postulate to say, oh, that's 3 units, and that's 3 units. I can measure them or take the absolute value of their difference. So yes, AB is congruent to CD. Next one, problem 2. Are they congruent? Nope. They don't measure the same. How about problem 3? You should have said, yep, they're both 6 units. Awesome. Last bit for today. On problem 4, what is the measurement of VW, line segment? Well, you should have said 31 minus 8 equals 23. Yay. How about VW here? Oh, it's 12. All right, how about VW here? VW. You should have said 75. Some of them. Awesome. Last, bookstore and a movie theater are 6 kilometers apart. A florist is located between the bookstore and the theater on the same street. The florist is 2.5 kilometers from the theater. How far is the florist from the bookstore? Well, you should have figured out that it's 3.5 kilometers. All right, that concludes our lesson. Thank your minds and your hearts, and thanks for bearing with this one a little longer because we had to sort of cut through some material. Have a wonderful afternoon. Bye.